Good. So let's start this lecture. This lecture is run by CMSA in Harvard University, jointly with Tsinghua University, the Math Center there. We had a few talks in China by Wilbur Schmidt and John Coates and myself. And now we have been doing it here. And we had several lectures already by Rubin in statistics, and by Joe Harris, and also Lydia today, this morning, and Simon Donaldson yesterday. And now we have Pavel Etingof, who has been in Harvard many years ago, now is a professor in MIT, and leading expert in quantum groups and all related subjects. We are very happy that he's going to talk about introduction to quantum groups. So, Pavel.
Okay, thank you very much. It's a big honor and pleasure for me to speak here. It is my second talk on Zoom, so I might make some mistakes that beginners make. So I apologize for those. So let me start. So the theory of quantum groups was developed in mid-1980s. It was developed kind of simultaneously in Fadeyev's school in St. Petersburg, and by Drinfeld, who was in Kharkov, and Jimbo, who was in Japan, in Kyoto. It came from mathematical physics, from the attempts to construct and understand solutions of the quantum Yang-Baxter equation, which arises in quantum field theory and statistical mechanics. And since that time, quantum groups has grown into a huge subject with deep connections to many other areas of mathematics and mathematical physics. And I will name some of them. One is representation theory, the Langlands program, which is at the border of representation theory and number theory, low-dimensional topology, category theory, enumerative algebraic geometry, quantum computation, algebraic combinatorics, conformal field theory, and integrable systems, and integrable probability. And there are some others. I will not be able to touch upon most of these, but I will be able to say a couple of words about some of them, maybe just one or two. For more, I certainly recommend a number of books on the subject. So there is a book of George Lustig, which has proved some very deep and difficult results about quantum groups concerning canonical basis. And then there are other books by Cassel, for example, by Janssen and other people. And my way of introducing quantum groups will be explaining their connection to tensor categories and to eventually maybe to low-dimensional topology. Because originally, so quantum groups came from mathematical physics, and originally people just worked with various formulas. So you define them by writing various relations, and it is not quite clear where these relations come from. They just work out to have nice properties. But actually, it is possible to introduce quantum groups quite conceptually, and this is what I'm going to try to do. And I apologize that the experts or even people who are somewhat familiar with the subject will not hear anything new. So the goal will be to review some ideas and examples in quantum group theory and briefly describe some of these applications. So let us start with the word quantum group, with the phrase quantum group. Where does it come from? So it comes from, of course, as you might guess, quantization of groups. And so let me recall what is quantization. So what is the basic setup of classical physics or classical mechanics? So in classical mechanics, we have a space of states, call it X, and we have an algebra A, which is algebra of observables, and which is the algebra of functions on X. And by functions, we can mean different things. If X is a finite set, it's just all functions, let's say complex valued. And if X is a manifold, which is more common in physics, this will be, for example, smooth functions. Sometimes you take holomorphic functions and so on. An example, basic example, is the symplectic plane R2. So this is the phase space, space of states. It has coordinates x and p. X is the coordinate and p is momentum of a particle on the line. So these x and p are examples of observables, as are any polynomials in x and p. For example, p squared over 2 is kinetic energy, and so on. And the set of quantum physics is that you replace this algebra A, which is a commutative associative algebra, by a non-commutative algebra, which is still associative, and sometimes called algebra of quantum operators. So I call it AH bar, because it often depends on the quantization parameter H bar, the Planck constant, and you recover the original algebra when this constant goes to 0. And in particular, P and X no longer commute. They are replaced with some elements of this non-commutative algebra, and they might satisfy, for example, this Heisenberg uncertainty relation, which is the commutator of P and X is equals to minus I H bar. And so now let's ask, what if the space X, the space of state, is a group? So this is not doesn't directly arise in the physics situation, but it actually connects to many things in mathematical physics. But purely algebraically, what kind of structure we will get? So, but we first have to understand what kind of structure the usual group is from that point of view. So our point of view was actually similar to one taken in, let's say, algebraic geometry, where we replace a space by the space of functions on it, which is an algebra. And we have to study this question from that point of view. So a group is equipped with an associative product, and it also has a unit, and all elements are invertible. So we have this system of axioms for a group, which is well known. And so what does it tell us about the algebra A of functions on G? Let's take, for simplicity, it to be a finite group. And then we see that, well, it's a commutative associative algebra with unit, but multiplication on G induces what is called a structure of a co-algebra or co-product. So more precisely, we have functions on the product G cross G can be written as a tensor product, functions on G with functions on G. And so one gets, so this map from G cross G to G gives us a co-multiplication or co-product on this algebra O of G. So it maps A to A tensor A. And the co-product is simply delta of F. It's an element of this O of G tensor O of G, which is the same as O of G cross G. So this means it's a function of two variables, each of which is in G. And the formula is that it is simply F of the product X and Y. And one can write it in this way. So there is this notation that is very useful in this theory, which is called Sweedler's notation. So if you do not want to write X and Y, you can write the delta of F is equal to F1 tensored with F2. But of course it is not, which is an element of this A tensor A. But of course, when we teach students linear algebra, and the first thing we teach them when we tell them about tensor products is that element of tensor product is not necessarily a product of two elements of the corresponding spaces. So there should be a summation. And indeed, this F1 cross F2 is a sum over I, F1I tensor F2I. But Sweedler, who wrote the first book on Hopf algebras, which is this structure going to be, he used this shortened notation, and at first it is confusing, but then you get used to it, and it's widely used now, so I'm going to use it as well. So what properties do these things have? So first of all, this map delta is an algebra homomorphism. Well, that's clear because it comes from a map of sets. So it's just a pullback for map of sets, so it has to be an algebra homomorphism. And also this algebra so it has co-unit and antipode obtained from the unit and inversion on the group, which are just these. Co-unit of F is just evaluation at the unit of the group, and antipode is induced by the inversion. And then there is an important property, which is that the coproduct is co-associative, which means that if you take a coproduct and then take coproduct of the first component, is the same as take coproduct and then take coproduct of the second component. It's a kind of dual condition to associativity. In some sense, it means that on the dual space A star, you have an associative product, and that's why it's called co-associativity. I see that there is a question, so let me read. Originally, Svidler Heinemann, but immortalized by Svidler. Okay, yes. So it's making my reference more precise. So this is co-associative. And then the second thing is this co-unit axiom. So co-unit, so this is really the axiom of unit for the group translated into the language of functions. And finally, the axiom of inverse for the group translated into the language of functions looks like this. So if you start with X, which is an element of your algebra, and take the coproduct, you end up in A tensor A. Then you apply the antipode either to the first or to the second component, and you still in A tensor A. And then you use multiplication, and you go back to A. And this is the same as a co-unit evaluated X. Well, if you like, you can say times the identity. So that's the axiom. And mu here is multiplication map. And so what is a quantum group? So a quantum group, or more maybe algebraically minded people would call a Hopf algebra, is a unital associative algebra A, which is not necessarily commutative, and which is equipped with those maps, delta, epsilon, and S as above, and has the listed properties. I should say that there is no commonly accepted definition of a quantum group. Some people would make this definition, and some people would reserve this name only for quantum groups that arise from quantization of actually classical Lie groups or ordinary Lie groups, which are definitely the most interesting examples. But for me, quantum groups today will be just Hopf algebras. And some people use even more general objects, such as quasi-Hopf algebras or weak Hopf algebras, and also call them quantum groups. And I should mention that this definition makes sense over any field or even any commutative ring, but I will work mostly over the complex numbers today. Also, usually it's assumed that the antipode is invertible, and I will do so. But I should mention that it is not true that it's always invertible under the axioms I mentioned. So it does not follow from the axioms. Although examples where it is not invertible are somewhat esoteric. Also, I will need notation for the opposite coproduct, which is the coproduct in which I switch the order of components. And finally, I want to say that it's convenient to view the unit of the algebra, not just as an element, but as a linear map from the ground field C into A, which sends 1 to this unit. And it will be clear why I want that in a sec. So here is a proposition. I will not prove anything here, but this proposition is the basic proposition about Hopf algebras. First of all, if A is a finite dimensional Hopf algebra, then the dual A star is also a Hopf algebra, and the operations on the dual are just dual to the operations on A. So multiplication of A dual is dual to the co-multiplication of A, and so on. If A is infinite dimensional, this is not quite right because, for example, if I take the multiplication on A and dualize it, it will give me a map from A dual, not to the tensor product of A dual with itself, but to the dual of the tensor product. And for infinite dimensional space, this is not quite the same thing. You get, the dual of a Hopf algebra in the infinite dimensional case will be a topological Hopf algebra. It is sometimes useful to think about such examples as well. Now, this epsilon is an algebra homomorphism. This is a property we had for free for groups, but here it follows from the axioms. And the antipode is actually, it was a homomorphism because it came from a map of sets, sending an element of the group to the inverse. But in this case, it will be, in general, it will be an algebra anti-homomorphism, and also a co-algebra anti-homomorphism. So it opposes the order of multiplication and also opposes the order of co-multiplication. So it switches delta to delta opposite. And finally, epsilon and S are uniquely determined by delta. And finally, if A is commutative, which is the case we considered before, or co-commutative means that its co-product is symmetrical, then antipode is involutive. Its square is the identity. And this is true even without the assumption that it's invertible. This theorem, this proposition actually, it's not completely trivial. It requires proof, but the proof is not too hard. So let's talk about examples. So first of all, the example that we considered, functions on a finite group. In this case, we have a commutative algebra A, and it will be co-commutative if the group is abelian. And there is a generalization of this example where G is an affine algebraic group. And then we can also take algebra of functions on G, but that algebra is now we take not all functions, but only regular functions on the algebraic group. This is still a commutative Hopf algebra. The third example is group algebra. So this is dual to the first example, and you can do it for any group, not necessarily finite. Then the coproduct of an element G will be just G tensor G if you take element of the group G. And antipode of G is G inverse, and epsilon of G is 1. So it's exactly like in the story we discussed before, except it's a dual story. And in this case, A is co-commutative. So the coproduct is symmetrical, as you can see. And finally, an infinitesimal version of this example, you take a Lie algebra, and instead of group algebra, you take enveloping algebra. Then coproduct of X of an element of Lie algebra is X tensor 1 plus 1 tensor X. And antipode of X is minus X. So you should think of this X as being log of G, or G to the exponential of X. Epsilon of X is 0. And so this example is also co-commutative. But these things formally they are quantum groups according to my definition, but they actually classical groups because they just come from ordinary groups or from Lie algebras, which are also obtained from ordinary groups. Here is a more interesting example, which is it's a true quantum group, something that everybody is going to call quantum group. And this is really the kind of the first non-trivial example in the subject. And much of today's lecture will be about this example. I will take Q, which is a complex number. And I assume that it's not equal to 0 or plus minus 1. And then we will define quantum groups UQ of SL2, quantum group UQ of SL2. It is going to be an algebra generated by E, F, and K to the plus minus 1, where the relations will be the following. So K, if you conjugate E by K, it multiplies by Q squared. If you conjugate F by K, it multiplies by Q to the minus 2. And if you take commutator of E and F, this is K minus K inverse divided by Q minus Q inverse. As we progress with the lecture, we will understand better and better where these relations really come from. And since it's a Hopf algebra, I want to define a Hopf algebra, I should define the coproduct and counit. And because coproduct is an algebra homomorphism, it is enough to define it on generator. Of course, then you will have to check that it preserves the relations. So there is something to check, but the definition is uniquely pinned down by saying that coproduct of E is E tensor K plus 1 tensor E, and coproduct of F is F tensor 1 plus K inverse tensor F, and delta of K is K tensor K. So the element K is called group-like because it behaves like a group element in this example number 3. And the counit then can be computed uniquely. The formulas are very easy like this. And finally, you can compute the antipode. So remember that we have this identity mu S tensor 1 delta of E equals to epsilon of E, which is 0. And so from that, you can, so you have to apply coproduct to E to get E tensor K plus 1 tensor E. Now you apply the antipode to the first component, for example. So then you will get S of E tensor K plus 1 tensor E. You multiply the components, you get S of E K plus E equals 0. And from this, you solve and get S of E is minus EK inverse. And in a similar way, you can get that S of F is minus KF. And S of K equals to K inverse. So we see that this is not commutative and not co-commutative. So that's the first truly quantum example. And also we should note that these relations, so why is it called UQ of SL2? Well, we didn't allow to set Q equals to 1. But because in that case, the denominator will blow up. But what you can do is you can at least formally set K equals to Q to the H. And so you will get Q to the H minus Q to the minus H here. And then you can take the limit Q goes to 1. And when you take that limit, if you apply formally the rules of calculus, Q to the H minus Q to the minus H over Q minus Q inverse is going to be just H, and you will get the relations H commuted with E is 2E, H commuted with F is minus 2F, and E commuted with F is H, which are the relations of SL2. And also I want to say that if you take square antipode, you can compute it as just conjugation by K. In particular, it acts on E with eigenvalue Q squared. So this means that in general, square of the antipode is not the identity if you're not commutative or co-commutative. So now I'm going to read a new question. What was the motivation for this definition of UQ of SL2? Yes, it's a very good question. It came out of mathematical physics. So like I said, people tried to understand solutions of the quantum Yang-Baxter equation. And there was a certain basic one having to do with the two-dimensional representation of UQ of SL2. This was the motivation. But actually, by the end of the talk, we will have a better idea why you write such formulas. Basically, one can show that this is the only deformation of enveloping algebra of SL2, which is a Hopf algebra deformation, up to some twisting, which is not important. And this is the only, this provides, we will discuss a lot the fact that quantum groups define tensor categories of representations. And this is the only deformation of the tensor category of representations of SL2. So that's the motivation. Yeah. Okay. And so, so now assume that Q is not, so then because it's a deformation of SL2, one can look at it at its representations, because we know that representations of SL2 are nice and very important. And it turns out that if Q is not a root of unity, then the representation theory of quantum SL2 is very similar to the representation theory of SL2, at least if you just want to classify representations. Here is the first proposition, which is analogous to the corresponding proposition for SL2, is that the finite dimensional representations are semi-simple. So because of that, if you are interested in finite dimensional representations, it suffices to classify irreducible ones. Well, there is a little difference with SL2, but it's very minor. It says the difference is that you have some, like not one, so SL2 has a unique one-dimensional representation, which is the trivial one, but quantum SL2 actually has two. So there is this character here, which kills E and F, but acts on K as -1 rather than 1, which would be for the trivial representation of a Hopf algebra is just the co-unit. But this chi is a little bit different. It sends K to -1 instead of 1. And we will say that the representation is of type 1 if eigenvalues of K on this representation are integer powers of Q. So then it will not be of type 1, and that it includes it. But we don't lose very much by that, because it turns out that if V is not of type 1, then it's always a tensor product of type 1 representation and this chi. So irreducible representation is either of type 1 or tensor product of that with chi. So eigenvalues of K are either powers of Q or minus powers of Q. So that's a very minor difference. And from now on, I will consider only type 1. The proposition is that there exists exactly one type 1 irreducible representation Vn of quantum SL2 of each positive dimension n+1. And the generator of this representation is V. It is satisfies the relations E times V equals 0, K times V is Q to the N times V, and it has basis F to the J times V, where J varies from 0 to N. And in this basis, the action looks like this. Well, obviously, F just ups this index by 1, and then K acts diagonally with eigenvalues Q to the N minus 2J. And finally, E times Fj. V is Q analog of J times Q analog of N minus J plus 1 times Fj minus 1V, where the Q analog of a number K is Q to the K minus Q to the minus K over Q minus Q inverse. So this is completely analogous to SL2. In the SL2 case, these Q numbers should be replaced by their limits at Q equals 1, which are just ordinary numbers J and N minus J plus 1. So there is a comment here. As I remember, Leningrad School suggested a different approach to defining quantum groups via function algebras. Why did Drinfeld and Jimba's approach become prevalent over the other one? Is it possible to understand solutions to quantum Yang-Baxter equation via the other alternative way? Yes, so that's a very good question. So the problem, so yes, you can understand solutions using the Fadeev-Reshetikhin-Takhtajan approach, which is based on quantum function algebras. And this approach was originally, so the problem with this approach is that it's not very convenient for Lie groups other than general linear groups, or maybe classical groups such as orthogonal and symplectic. While the approach of Drinfeld, which I will stick more to, works for any Kac-Moody algebra. However, there is a theory of quantum function algebras for any group, which is very useful and which is a generalization of what they did in the Leningrad school. So now let me talk about tensor products. So that's the fundamental structure of representations of Hopf algebras. Recall that if you look at representations of a group or Lie algebra, they are endowed with tensor products. So there is if you have a representation of G, a group, two representations, V and W, you can tensor them by just tensoring together the corresponding operators. And similarly for Lie algebras, but for Lie algebras, instead of tensoring together the operators, you should take the first one tensor identity plus identity tensor the second. This is what you get if you take the derivative of this. And similarly, one can define the tensor product of representations of a Hopf algebra. And that's actually basically what Hopf algebras are good for. This is why they're useful and interesting, because they give rise to a tensor structure in the category of representation. So the formula is just this. Well, so this is pi of G tensor G, and this is pi of X tensor 1 plus 1 tensor X. And recall that G tensor G is just a coproduct of G, and X tensor 1 plus 1 tensor X is just a coproduct of X. So, so therefore, we should just replace this with the coproduct, and the formula is pi of the tensor product applied to X is the following. You take the coproduct of X, and then you apply to it pi V and pi W. So if you write it in terms of Swidler's notation, it looks like this. And this should be A rather than H. So one can regard this category of representations of A as the category equipped with the tensor product by functor, which is a functor which attaches to a pair of objects, a new object X tensor 1. And this allows you to think about Hopf algebras in a categorical way. So this product is in fact unital. So there is a trivial one-dimensional representation, which is given by the co-unit, as I mentioned. And it has the property that when you tensor it with any object X, you get the same thing, X. And also, this tensor product is associative on isomorphism classes. So if you tensor X and Y, and then tensor it with Z, is the same as X tensored with Y tensor Z. Well, it's obvious for vector spaces, but also it's true for representations because coproduct is co-associative. So this is really means that on this space, and there is a natural identification of this space and this space, and the action after this identification becomes the same. Okay, so and so the C is therefore a category with a unital tensor product associative up to an isomorphism. Unfortunately, this notion is not very good. In fact, you cannot say much about such categories. And the problem is that we're basically saying these objects are isomorphic or equal, their isomorphism classes are equal, but in category theory, this is not a good way to do things. In category theory, if you have some objects which are isomorphic, you should actually make the isomorphism a piece of data and impose some axioms on it. So it turns out, however, that in natural examples, that more structure is actually present. A lot more structure is present, and it's just a little bit less obvious. So much better notion than this notion here, which is so bad that it doesn't even have a name, is obtained if you follow the general yoga of category theory, as I mentioned, and you don't just simply say that these things are isomorphic or equal, but make this isomorphism a part of data and impose some coherence conditions. And this leads you to the notion of monoidal category, which was developed by McLean in the 60s, and or even earlier maybe, and which plays a fundamental role in modern mathematics in many areas. So let me go over what that notion is. So we should equip C with what is called an associativity isomorphism. So this is an isomorphism between product this way and this way. It should be functorial in X, Y, and Z. So it should commute with morphisms in the X, Y, and Z components. And it should also satisfy the pentagon identity. So this is the fundamental identity of the subject, the pentagon identity. In this identity, I consider products of 4 things, but to make the picture nicer, I omit the tensor product signs. And also the maps here are defined by this associativity. So for example, if I start from this vertex here, then going down this arrow means that I look at objects X, Y, Z, and T, and I move the outer parentheses to the right. And then here, I consider objects X, Y, and ZT, and move these parentheses around X, Y also to the right. And here, but you can also do differently. You can move the parentheses inside, instead of moving outside parentheses to the right, you can start with the inside ones. And then you are led to go on the other side of this pentagon and arrive in the same place. And the requirement is that these 2 ways should be the same, which means that the diagram should be commutative. Also, there should be a unit object, and it should be isomorphic to its square. And the functors of tensoring with this object should be outer equivalences. Well, it's a kind of minor point. The main structure is associativity in the pentagon. And the category C with such structures and properties is called the monoidal category. The reason is that it's a categorification of monoid. So in a monoid, what is a monoid? It's the same as a group, except we don't have inversion. So we have multiplication, which is associative, and we have a unit. And here also is the same thing, but we have that at the level of categories here. And that's why we have to specify all these additional structures. So we are 1 step up from monoids. So it's a categorification of monoids. This is why it's called monoidal category. So we see that for a Hopf algebra A, the category of representations of A is a monoidal category. And this alpha X, Y, Z is just the most natural thing you can imagine. It maps X tensor Y tensor Z to X tensor Y tensor Z. So it's kind of almost trivial thing. There is a similar examples. So representations are modules, but you can also consider comodules. So comodule means that, module means that you have a space V and a map from A tensor V to V. But comodule means that you have a space V and a map from V to A tensor V. So in a sense, it defines an action of the algebra A dual. We know that the dual to a Hopf algebra is a Hopf algebra, in particular algebra. And even in the infinite dimensional case, it still is going to be an algebra. And so we can have comodules, and you can tensor them very similarly, because in the finite dimensional case, it's just modules over A star. So we tensor them, and that also forms a monoidal category. If you have a finite dimensional algebra, then it is simply the same as the representations of modules over A star. Also, if G is an algebraic group, then more or less by definition, algebraic representations of G is the same thing as a finite dimensional comodule over this algebra of regular functions O of G. And now I want to discuss duality of representations of Hopf algebras, which generalizes duality for group and Lie algebra representations. And this is the structure that is going to have to do with the antipode. So let's recall first the classical story. Okay, so there is a question: how much do comodules differ from the modules in the dual of the dual in the general infinite dimensional case? Yeah, so comodules are less general because if you have a map from A dual tensor V to V, this doesn't necessarily give rise to a map from V to A tensor V. So comodules are much less general, but they are much more convenient to work with also. Okay, so so there is a notion of dual representation for Lie algebra and for a group, which is well known. And by analogy with that, we define the notion of dual representation of a Hopf algebra. So it will be realized on the dual space 2x. But here we are going to get two different notions. Because for groups, remember, action of G on the dual representation is the adjoint of the action of G inverse on the original representation. And for Lie algebras, it is the action of X on the dual representation is the adjoint of the action of minus X on the original representation. So this means that it's actually about the antipode. But for Hopf algebras, as I mentioned, square of the antipode is not the identity. So this means that we have two ways of defining it. The left dual when you use the antipode itself, and the right dual when you use the inverse of the antipode. These terms are used because both of these are x dual and x right dual and x left dual are, so we have a functor. If you have x, you have a functor of tensoring with x. And it turns out that left dual is the left adjoint of that functor. Tensoring with left dual is left adjoint of that functor, and tensoring with right dual is right adjoint. And so if you have this pair, x and the right dual, then you have what is called evaluation morphism. So in the case of Hopf algebra, so you have evaluation morphism, which is just taking the pairing. And but for finite dimensional representation, you also have a dual map, which is from 1 to x tensor x dual, which sends 1 to the sum of some basis xi, here tensored with the dual basis xi dual. And so there is a pair of functorial isomorphisms. So if you first take left dual and then right dual, or first take right dual and then left dual, you get back the same thing, and functorially so. So I want to axiomatize this structure in the setting of monoidal categories. So an object of monoidal category is called left dual to x. Y is left dual to x. If there exist morphisms like I wrote, y cross x to 1 and 1 to x cross y, called evaluation and co-evaluation, such that you have the following properties. So if you start with x, and then you, so x is 1 tensor x. So, and then you can apply to 1 this co-evaluation, and you end up in x, y, x. Then you can apply this alpha map and goes to x cross y, x. And then you can do nothing to the first component, but then evaluate here. So you get to 1, x tensor 1, which is x. And the composition is a map from x to x, which should be the identity. And there is a similar diagram for y, and the composition should also be the identity.
There's a question.
Yeah, there is a question. Dari asks, adjoint with respect to inner or outer Hom. Well, it's what I mean is that for finite dimensional spaces, you have Hom. With respect to both Homs. So for representations, Hom of V tensor X to Y is the same as Hopf from X to V dual times Y. But one has to be a little careful with this and with finite dimensionality and so on, but basically it's like that. If Y is a left dual to X, then we have a functorial isomorphism Hopf from Z to Y is the same as Hopf from Z tensor X to 1. So the functor Hopf from Z to Y is determined by X completely. And this means that Y is determined by X completely up to a unique isomorphism by Yoneda lemma. So left dual, if it exists, is unique. Similarly, you define the right dual. And of course, the right dual is called that way because you put the star on the left. You have to remember that. If X is the left dual of Z. So operation of taking left and right dual are inverse to each other. Because one is defined using antipode, the other is defined using the inverse antipode. And a left dual, so again, it's also unique if it exists. And then the main definition, an object is rigid if it has both the left and the right dual, and the category is rigid if all its objects are rigid. So all objects have left and right dual. And the category of finite dimensional representations of a Hopf algebra is a rigid monoidal category. You need finite dimensionality because, like I said, this co-evaluation map from 1 to X tensor X dual is defined by sending 1 to the sum of some basis xi tensored with xi duals. And this sum will be infinite if your representation is infinite dimensional. So this is not going to make sense. So for rigid, you need to have finite dimensional representations. So here are some examples of rigid monoidal categories. So for example, if you have a finite group and take algebra of functions on this group, it's what do representations look like? This is a commutative semi-simple algebra. So its reducible representations are one-dimensional and they are parameterized by group elements, G. So I'm just going to call them that way, G. And the tensor product in that case, it's easy to check, is just the ordinary product of group elements. And dual is just inverse. Both duals, in fact, are inverse. In this case, square of the antipode is the identity, so left and right dual are the same. And so this rep F of A is rigid monoidal category, and it's denoted by vec G, because it is really the category of G-graded vector spaces. Because what is a general object of this category? It's a direct sum of such G's. So every G occurs with some multiplicity, which is a vector space. And so we can think of this vector space sitting at this G. So you'll get like a graded vector space by the group G. And it makes sense actually for any group G, not necessarily finite. You can consider finite dimensional graded vector spaces, and then you can tensor them by using convolution, and that's what this thing does. And in fact, so this doesn't have to do much with what I'm talking about, but I want to bring it up to illustrate that this associativity map is not a trivial object. So give an example where the associativity map is manifestly non-trivial, because it was something kind of almost trivial in the example of Hopf algebra. So this is just a twisted version of the previous example. So what you do is, instead of saying that the map from here to here, the associativity map is just 1, we can make it to be some scalar, alpha G H K. Because the maps from here to here is just C. So we can make it some invertible number, non-zero number, alpha G H K. And then the pentagon relation turns out to be equivalent to saying that this alpha is a 3-cos cycle of the group G. And so if you have a 3-cos cycle, you can equip this category with another structure of a rigid monoidal category, which will have the same tensor product functor, but will have a different associativity isomorphism. And so you will get a different category. And this will be denoted by vec G alpha. Now so there is a question. A G-graded vector space is a functor. I'm not sure I understand. Maybe you can clarify the question. And then there is by loosening the pentagon more, what extra structures can we see? Yeah, there is a theory of higher categories where pentagon is not required to be satisfied, and then indeed you can do this, and that leads to very interesting things. But this is beyond the scope of this talk. And the question, a functor from G to vec. Well, I mean, the best thing to think about it is just a bunch of vector spaces. Graded vector space by G is just a bunch of vector spaces which are labeled by group elements. So I wouldn't think of it as a functor, at least I don't see right now. So the twisted version then is vec G alpha. And now I want to talk about monoidal functors, because, for example, we want to talk about two monoidal categories being kind of the same. So let's C and D be monoidal categories. So a functor f from C to D is called a monoidal functor. If but being a monoidal functor is a structure, not a property. So you need to fix some data. One thing is just a property that it should map the unit to the unit. But then it should also be equipped with this thing which is called tensor structure, which is a functorial isomorphism from f of x tensor f of y to f of x tensor y. And this structure, as always, is required to satisfy some property. And this property is this diagram, which basically means that, that this tensor structure map relates associativity in one category and in the other. So the functor, to even say that it preserves associativity morphism, we need this J, and then we can write this diagram, and this diagram is required to be commuted. And a monoidal functor is called an equivalence of monoidal categories if it is an equivalence of categories. In this case, you can construct the inverse or quasi-inverse, which will also be a monoidal equivalence. So monoidal categories which are equivalent are kind of the same for all practical purposes, and that's why this is an important notion. So, so here is an example which is kind of somewhat non-trivial. So I told you that you can define a monoidal category structure on the category of G-graded vector spaces. If you have a 3 cocycle on your group G. So you have category vec G alpha and vec G beta. Now suppose you have 2 3 cocycles and look at the identity functor from this category to this one. Well, this is not yet a monoidal functor because I didn't tell you what this J is. And in fact, if alpha and beta are arbitrary, there will be no tensor structure satisfying the axiom above. However, if the ratio of alpha and beta is a coboundary, it's a coboundary of some function J, GH, of 2 elements of the group, then we can use this J as a tensor structure, and it will define a tensor functor, a monoidal functor, and in fact, equivalence of monoidal categories from here to here. So, so it admits a monoidal structure if and only if cohomology classes are the same. So in fact, these categories up to equivalence are classified by the third cohomology of G with coefficients in C star. And in particular, vec G alpha is equivalent to vec G if and only if alpha is equal to 0 in the, or 1, if you like, in this group, H3 of G with coefficient in C star. So now I want to talk about the universal R matrix of quantum SL2. And this discussion starts with pointing out that because coproduct in a quantum group is not co-associative, in general, then we cannot expect that X tensor Y is isomorphic to Y tensor X. For example, in the example I just considered, G tensor H is just the product in the group GH, and that doesn't have to be equal to HG because the group may be non-abelian. However, sometimes even when delta is not equal to delta opposite, we still have that the tensor product X tensor Y is isomorphic to Y tensor X. It's just that the isomorphism isn't always just the flip map. There is a question. Do all monoidal categories come from representations of a Hopf algebra? The answer is no, not all. In fact, it's a very good question. So this category vec G alpha, when alpha is not equal to 0 in this cohomology group, this category does not come from representations of a Hopf algebra. Okay, so here is an example when that happens. We still have this isomorphism even though the coproduct is not co-commutative. So suppose you have a quantum group where UQ of SL2, where Q is not a root of unity. And then, so Drinfeld defined the universal R matrix. So you write this kind of complicated looking formula. So it's an infinite sum. Let's see if we understand what things mean in this sum. So this e to the k, f to the k, it is clear. And then this is just some number, q minus q inverse to the k divided by the k q factorial. So q factorial is just defined analogously to ordinary factorial. It's a product of q numbers from 1 to k. This is also clear. And then there is this q to the h tensor h. This R makes sense as an operator on X tensor Y for any finite dimensional type 1 representations. So that's because the sum terminates, because operators E and F are nilpotent on finite dimensional representations. Yeah, there is somebody points out so there is an error here. There should be h tensor h over 2. There is a misprint. Q to the h tensor h over 2. There is also a question. The R matrix that you mentioned is the same thing as the R matrix structure in integrable systems. Yes, there are classical and quantum R matrix. This is a quantum R matrix. There is also classical limit of it, which is classical R matrix, and both of them arise in integrable systems. Classical R matrices in classical integrable systems, and quantum R matrices in quantum integrable systems. Okay, so yes. So this is over 2 here, and the sum terminates, so that's fine. And then I have to explain what this thing is. So Q to the H tensor H is equal to acting on X tensor Y is Q to the lambda mu, but it needs to be over 2 X tensor Y if X and Y have weights lambda and mu. So this means that I have to extract the square root of Q to define this object. Then the theorem of Drinfeld is that the operator C, which is ordinary swap, composed with the R matrix, which is a fairly non-trivial operator, gives rise to an isomorphism of representations, X cross Y to Y cross X. So the point is that if we don't use the R matrix, this is of course an isomorphism of vector spaces, but not of representations, because coproduct is not symmetric. to compensate for the non-symmetry of the coproduct, we need to introduce this R. And then it's possible to compensate and you get a morphism of representation. So this means that R times delta of A equals to delta opposite of A times R on this X tensor Y for any element A in the quantum group. And in fact, you can show that this identity holds in some completion of the tensor square of the algebra UQ of SL2. So here is a prototypical example of a monoidal category where this tensor product is symmetrical up to isomorphism, so commutative up to isomorphism. And this is called the Drinfeld center of a monoidal category C. So I will have a discussion of this category theory business now, because I want to explain how to obtain this formula, because so far it looks like it's been taken out of a hat and there is no motivation. But in fact, it can be motivated very well by category theory, and they will let me explain how. So what is this Drinfeld center? So Drinfeld center, which was defined by Drinfeld and also independently by Majid in the 80s, is another category which can be attached to any monoidal category C. And it is the category of pairs Y, phi, where Y is an object of the original category C, and phi is a functorial isomorphism, which is a collection of maps phi sub x from Y cross X to X cross Y, which satisfies the following commutative diagram. So it should basically, so this is a phi is a way of swapping Y with other objects. And it should satisfy this diagram. What is the kind of meaning of this? Why is it called center? Well, as we know, monoidal categories are analogs of monoids, and monoid has a center, which is elements, that commute with everything. But in category theory, we should not just say that they commute with everything, but we should give a structure that allows them to commute, which is this phi x, and the structure should be subject to some axiom, and this is the axiom. There is a question, does the R matrix approach only work for quantum SL2 or for other quantum groups? Yes, it works for other quantum groups as well, and that's why it's so good, and so that's why I'm talking about it. Anyway, so morphisms of such pairs are just morphisms in C, which also preserve this phi. Then this Drinfeld center is a category, but it actually has a monoidal structure. You can also tensor elements of objects in this category. Because if you know how to swap Y with objects and Z with objects, then you know how to swap Y tensor Z with objects. So if you want to swap Y tensor Z with X, then you first swap Z with X, and then you swap Y with X. So you make a composition, which is written here, where I suppress the associativity maps. So this pentagon relation allows us not to worry too much about these associativity maps when we do formal calculations, and I'm going to suppress them to make the diagram smaller. So there is a monoidal structure here, and so I only described how to tensor, and there is also a natural associativity, which is basically the associativity of our underlying category C. And also we can forget this phi, so attached to Y phi just Y, and this is the forgetful functor, which is a monoidal functor from the Z of C to C. And also actually it's not just an arbitrary category, but this is a category where this property that we wanted holds. The tensor product in one order and in the other order are actually isomorphic. And they are actually isomorphic canonically and in two different ways, in fact. So one way is the following. We just take phi sub Z. So this means that to swap, because if we know how to swap Y with any object and Z with any object, then we know how to swap Y with Z. So if you know how to swap these objects with objects of C, then we know how to swap them with each other. And we could do it in two different ways. one way we can do a right swap of y with z, using that y can be swapped with anything, or we can do a left swap with z with y, knowing that z could be swapped with anything. And those things are inverse to each other, but they are different. So this means if you swap twice, you don't necessarily get what you have. You don't necessarily get the identity. So, this gives rise to the action of the braid group on the tensor power of any object V of our category. So let me recall what the braid group is. So braid group is the fundamental group of Cn from which we remove the diagonals modulo the symmetric group permuting the coordinates. And as a group given by generators and relations, it's generated by swaps of 1, 2, 2, 3, 3, 4, and so on, such that swaps commute if I minus j is at least 2. And also, if they're 1 apart, you get this cubic called braid relation, Si, Si plus 1, Si equals to Si plus 1, Si, Si plus 1. If you want to get the symmetric group, you have to also mod out by the relation that Si squared equals to 1. So we have a proposition that there is an action of the braid group on V to the n, which is defined by rho Bn to automorphisms of V to the n, which sends Si to the map C, which is defined here, acting on the I and I plus 1th component. And as I mentioned, if you do this thing twice, you don't get the identity. So this does not give, in general, a representation of the symmetric group. It only gives a representation of the braid group. And this is why this business is related to low-dimensional topology, because the braids are related to knots. And so we get knot invariance and so on. If I have time, I may say a couple of words about that. So how to prove this theorem that we do get these relations? So it turns out that these relations follow from 2 diagrams. I'm not giving a complete proof, but just the idea. So we have the hexagon relations. And the relations are the following, that if you want to swap x with y tensor z, you can do it in stages. So first swap it with y and then with z. And similarly, if you want to swap z to the left with x tensor y, you can do it in 2 stages as well. So again, suppress alpha, and maps are given by this C. And the reason they're called hexagon relations is because if I hadn't suppressed alpha, there would also be 3 alpha maps in each of these diagrams, and altogether it would be a hexagon. So this motivates the definition of a very fundamental notion, which is called a braided monoidal category. So braided monoidal category is a monoidal category endowed with a functorial isomorphism of a tensor product to the opposite tensor product, which means for every x and y, x tensor y to y tensor x, which satisfies the hexagon relations. So I remind you the hexagon relations are these. And thus we obtain the theorem that the Drinfeld center, Z of C, is a braided monoidal category. Moreover, every braided monoidal category is a braided subcategory of its Drinfeld center, because you can include C into Z of C by sending X to X and CX question mark. So this map C is called the braiding map. And if you have a braided category, then for every C, for every X, you already have a way of swapping X with everything, which is the C corresponding to this X. And that gives you a functor this way. And if you compose it with a forgetful functor, you just get the identity functor. So this means that this is an inclusion of C into Z of C. And this is why I said that the Drinfeld center is a prototypical example of a braided category, because any braided category can be seen inside its own center. And an example that is a little more down to earth is that the category of finite dimensional type 1 representations of UQ of SL2 form also a braided monoidal category with C given by P composed with R, which is the map that I talked about before. So, and as a consequence, this R satisfies the quantum Yang-Baxter equation. So this equation is, so if you have 3 representations, X, Y, and Z, then you can define 2 operators. So R12 means that R acts in components 1 and 2. R13 means that it acts in components 1 and 3. And R23 means that it acts in 2 and 3. And then so there is a question, why is it Cx, Yz equal to Czy inverse for Y and Z in the center? So this is a lemma to prove, but it follows from functoriality. So I have this Yang-Baxter equation, which says that your product in one order equal to the product in the other order. So this is the equation that the whole business started with. And it really follows from the fact that in the braided category, we have this braid relation, action of the braid group, B3 on a tensor product of 3 representations. So on a tensor cube of representation, and you have this thing here. So if you have 3 different representations, you should take their direct sum and apply what I said to that V equal to that direct sum. I should mention that a braided category is called symmetric if double swap is the identity. And we know a lot of symmetric categories, because if you have C is the ordinary swap, then the double swap definitely will be the identity. So we have representations of a group and representations of a Lie algebra. These are symmetric categories. But the center of C is almost never a symmetric category. And this representations of UQ of SL2 is also not symmetric. Now, there is a relationship between these 2 results. So far, the center is some abstract categorical construction, and this UQ of SL2 story is a concrete theorem, which looks non-trivial because we have this rather complicated formula for R, and then we will have to check some hexagon relations for this R, which certain non-linear quadratic equations in this R. It looks like a long calculation, and in fact it is if you actually try to do this calculation. It's relatively long. But it turns out that you don't have to do this calculation, because in fact, this theorem here, it follows from this one, and you can get, moreover, if you didn't know the formula for R, you could automatically obtain it just from this categorical story. And this is what I want to explain. So I want to, so for this purpose, let's calculate the Drinfeld center of the category of representations of a Hopf algebra. So suppose we have an element of this Drinfeld center, an object of this Drinfeld center. So then we can, in particular, so what kind of structure do we have in this Y? First of all, it's a module over A, but also it's, it has a swapping property. So we can swap it with any A module. And but any A module is a quotient of a free module. So it's enough to know how we swap it with the free module. So we can swap it with A. So there is some map here. But now what is Y tensor A? Y tensor A is just the induced module from C to A of Y. In particular, it contains a copy of Y. We can restrict this phi to Y, and we get a map from Y to A tensor Y. And this map turns out to be a co-module structure. And moreover, there is a compatibility condition between them, which you can get from the axioms of this center. and which says that if you compute tau of A times Y, where A is an A, this is the same as this expression using this Sweedler notation, where tau of Y is written as Y1 cross Y2. And this A1, A2, A3 are components of the double coproduct of A. And it doesn't matter whether it's 1 cross delta or delta cross 1 because it's co-associative. And so this is what is called a Jeter-Drinfeld module. So a Jeter-Drinfeld module over A is an A module Y, which is also an A comodule with this coaction satisfying this compatibility condition. And the category of such modules is denoted by YD of A. And we have a proposition that the category of representations of A, if you take its center, the center of representations of A is the category of Jeter-Drinfeld modules of A. Now, if A is finite dimensional, then this can be described in a more explicit way, because an A comodule is the same thing as an A star module. So this category, Jeter-Drinfeld modules of A, can be realized as the category of modules over some algebra generated by A and A dual with some way of commuting them with each other, with some commutation relation. So the commutation relation will come from the compatibility condition. So this proposition that we have here is that for a finite dimensional algebra A, there is a Hopf algebra D of A, isomorphic as a vector space to A tensor A dual, because we know how to swap A and A dual, such that there is a monoidal equivalence of Jeter-Drinfeld of A and representations of this algebra D of A. And this Hopf algebra is called the Drinfeld quantum double of A. So again, there is a definition of this quantum double. So you can actually realize it as a tensor product A and A star. And these are included as Hopf subalgebra, except that coproduct on A star is opposite. And then there is a swapping law, how to swap an element of A with element of A dual. And this gives you this formula, which is in Drinfeld's paper, and which is hard to understand, or even harder to think about how you can guess this formula, unless you go through this category construction. But you can define it purely algebraically in this way. So the double is just a tensor product with multiplication. A and A star are sub-Hopf algebras, and commutation of A and A star op is given by this formula. Now, we know that this YD of A is a braided category because it is the center, and therefore there should be a way to express that in terms of this double D of A. And this is addressed by the following theorem of Drinfeld. So the braiding on this category is given by the universal R matrix. So C equals to P composed with R, where R is an element of this D of A tensor D of A, which actually lies in A tensor A star opposite. But this is not the first component of D of A. This is kind of spread out. So the first A sits in the first D of A, and this sits in the second D of A. And it's given by the universal R matrix, which is very easy to write down. You just take some basis AI of A and the dual basis AI star of A star. And then you take this sum. So basically it's the canonical element in the product. And that makes sense in the finite dimensional case. And so in particular, this implies that this R, if you write it this way, satisfies this quantum Yang-Baxter equation. And again, this should be A. The commutation relation between A and A star is uniquely determined by this equation. So in fact, you can check that in the first component, you get only elements of A. In the third component, you get only elements of A star. But in the second component, you get in the first expression on the left-hand side, A and then A star, And in this expression, A star and then A. Or actually it's the other way. This has A times A star and this has A star times A. So actually this is a way to write down this commutation relation, which I gave you on the previous slide, which is here. So this quantum Yang-Baxter equation is basically equivalent to that. And so let me give you a couple of examples. First of all, we have a group algebra of a finite group. And in this case, the double is the semi-direct product. So you take functions on the group and the group algebra, and you take the smash product where the group acts on itself by conjugation. So it turns out that so this is our A and this is our A dual, but the commutation relations between them is expressed just by saying that G acts on itself by conjugation. And then the R matrix looks like this, where delta is the delta functions of the group. And you can check that this satisfies the quantum Yang-Baxter equation. It's quite easy. But here is a more interesting example, which takes us closer to the topic of discussion of quantum groups. So suppose L is a positive integer, which is odd, and Q a primitive root of unity of order L. And let us take the first non-trivial example of a Hopf algebra, which is a finite dimensional Hopf algebra of dimension L squared. And it is generated by E and K, where K is invertible. And the relations are KE equals to Q squared EK, and E to the L equals 0, and K to the L equals 1. And the coproduct is defined by these formulas. Delta E is E cross K plus 1 cross E, and delta K is K cross K. So it is the same story as for quantum SL2, except two things. We don't have F, and also it's truncated. So we have a root of unity, and we have this nilpotency condition and the condition K to the L equals 1. Then we can try to compute there is an antipode which you can easily compute. So you can define the double, and it's a Hopf algebra of dimension L to the 4th. And actually you can compute it. It's not very hard, a very nice exercise. And it turns out that it's a tensor product of two things. Well, of course, tensor product of Hopf algebras is a Hopf algebra. So it's a tensor product of two Hopf algebras. One of them is just the group algebra of Z mod L. And the other is D0. And this D0 actually is of dimension L cubed. And it's generated by EF and K plus minus 1 with relations as above. And there is also relations with F. So KF is Q minus 2 FK. And EF minus FE is K minus K inverse over Q minus Q inverse. So this means, and the coproduct is given by the above formulas. And also for F, delta of F is F cross 1 plus QK inverse cross F. So now you note, if you look at these formulas, that this D0 these are exactly the same equations as for quantum SL2, except that we have these truncation conditions. So this is a truncated version of quantum SL2. It's a quotient of quantum SL2 by the relations E to the L equal F to the L equal K to the L minus 1 equals 0. And you can mod out by these relations, and this will preserve Hopf algebra structure if Q is a root of unity, primitive root of unity of order L. And this is called the small quantum group. And it was introduced by Lustig, actually, for any simple Lie algebra, and it's denoted by small uq of SL2. And by virtue of the construction, this D0 has a universal R matrix, which comes from that for D, because D projects onto D0. This R matrix, you can compute it, and actually it's given by the same formula with the same misprint here, H over H tensor H over 2, except that the sum is truncated at L minus 1. So that's how this formula comes out. And in fact, the punchline is that for general Q, when this thing is infinite dimensional, this can be constructed by some kind of infinite dimensional quantum double. This naturally produces both the commutation relation between E and F. So that relation you don't have to guess. it comes out of the construction, and also the R matrix comes out, and also the fact that this thing satisfies the quantum Yang-Baxter equation, which looks like a scary calculation. You don't have to do this calculation because that follows from category theory. If you don't believe in category theory, you can check in the calculation. After a few pages of computation, you will get that it's true. Similarly, one can construct higher rank quantum groups. So let me just go over that very quickly. So in that case, you have a Cartan matrix for a simple Lie algebra, Aij, and there are symmetrizing numbers, Di. So this means that the matrix Di times Aij is symmetric. And then we start off with the Hopf algebra UQ of B+, which is a quantization of the Borel subalgebra, which only has E's and K's, but not F's. So it's generated by EI and KI plus minus 1. And the relations are just basically kind of exponentiation of the relations for the ordinary Borel. And ordinary Borel also has Serre relations. So coproduct is defined as before for each I, as for SL2. And there are also quantum Serre relations. I didn't write them here, but you can actually, again, say what they are without writing any formulas. They are the most constraining relations you can impose, preserving the Hopf algebra structure without killing any of the EIs. So it's the largest, if you define first the Hopf algebra with these relations, it is going to be free with respect to EI, so the EIs do not satisfy any relations. And then you can take the largest ideal, which doesn't kill any of the EIs, which doesn't contain any of the EIs, and which is a Hopf ideal, which means quotienting, but it preserves the Hopf algebra structure. Then this will be generated by these Q-deformed Serre relations, which look the same way as ordinary Serre relations, except that the binomial coefficients that occur in Serre relations are replaced with quantum binomial coefficients. And then what one can show, this is somehow one of the main results of Drinfeld, that this, you can take the quantum double of this thing, and this will give you almost the quantum group UQ of G for G. So more precisely, you will have, because Borel contains the torus, so the dual will contain F's and K's, and you will have two sets of K's. So you have a redundant copy of the maximal torus. You have to mod out by that copy, so you'll get a tensor product of UQ of G with that copy. You have to kill that copy, and that gives you UQ of G. And then you have to say, so the algebra that you will get, it has Fi, additional generators Fi, which satisfy this Serre relation. And then there are commutation of E's and F's, and those come from the commutation relations between A and A dual. And finally, so these commutation relations and the R matrix, which is now much more complicated for other Lie algebras, are nevertheless produced automatically by the double construction. And in fact, this works much more generally for any symmetrizable Kac-Moody algebra. And to wrap up, I want to give an example how this applies to low-dimensional topology and talk about the Jones polynomial. So the Jones polynomial is a very powerful invariant of knots, which was found by Van Jones in the 80s, and it fits very nicely into this theory. So more precisely, it is well known that any knot K can be obtained by closing a braid. So a braid means that you have some strands, and then you just attach beginnings to ends. It can be obtained by closing many different braids, but let's choose one. On the other hand, we know that this braid acts in a tensor power of V, where V is a two-dimensional representation of quantum SL2. And then we can compute the trace of B on this representation, the character value for this representation of the braid group. And it turns out it's a function of Q because everything depends on Q. And this turns out to be the Jones polynomial up to some normalization factor. So it does not depend on the choice of B, which is a non-trivial statement, and coincides with this Jones polynomial of this node. And if you take other representations, VI, for I greater than 1, you will get what is called colored Jones polynomial. And if you pass to other simple Lie algebras, you will get even more powerful invariants of nodes, which are called Reshetikhin-Turaev invariants. Among them, the most famous is the so-called Hopf polynomial, which you obtain for Lie algebra SLN and vector representation, or colored Hopf polynomial, which you obtain for general representations of SLN. Okay, thank you very much. So I am finished. So there is a question. When you say it works for Kac-Moody algebra, what is the underlying tensor category? And what is the tensor product? Okay, so the underlying tensor category. So first of all, already for SL2, you can take a bigger category, which would be a category, so-called category O, which are which will include Verma modules, for example. Though that category is not rigid, we don't have duality there, but it is still a braided monoidal category. For Kac-Moody algebra, similarly, you can take category O, or you can restrict to category of so-called integrable representations, which are direct sums of finite dimensional representations for each SL2 subalgebras corresponding to simple roots. And tensor product will be defined in the same way. We have coproduct, and tensor product is just usual tensor product of vector spaces with the action of the Hopf algebra defined by the coproduct. So that answers. So there are variants of what kind of category we can take. And in the case of Kac-Moody algebras, which are not finite dimensional, you will never get a rigid category, but you will get a braided monoidal category. There is another question. The R matrix is a great tool. Do you know any relationship to the Lux pair which guarantee integrability? Also the relation to Hamiltonian Dirac structure. Yeah, there are many papers about that, especially for classical R matrices, which I didn't talk about. So there is a, quantum groups have a quasi-classical version. So like I said, it's a non-commutative algebra, which is a deformation of a commutative one. I only considered that commutative algebra, but in fact, we can consider what happens to the non-commutative structure in the limit, take the first derivative, and that's called Poisson structure. And in the case of quantum groups, this is give you something which is called Poisson-Lie group. That's a very beautiful and important notion. A Poisson-Lie group is a Lie group with a Poisson bracket such that multiplication is a Poisson map. And there is a theory of Poisson-Lie groups created by Drinfeld, and it's strongly related to all these things here. Classical R matrices naturally fit into that. There is a paper of Semyonov-Tanshansky, which is called What is a Classical R matrix? And he explains very well the connection between R matrices and integrable systems. There is also a connection between quantum R matrices and quantum integrable systems, such as, for example, quantum spin chains, XXX model, and so on. There is another question, another interesting phenomenon if we do this procedure for Kac-Moody algebras of affine or indefinite type that do not happen in the finite case. Yeah, definitely there are, especially for affine algebras. There is a very interesting theory of finite dimensional representations, which is not the same as for classical Lie algebras, and which is subject to many studies. It's related to cluster algebras and to mathematical physics of all kinds and so on. And this is not conformal theoretic. Okay, so I was answering the question about what is the tensor product for Kac-Moody algebra. This is not the conformal field theoretic tensor product, which is fusion product. Yeah, that's right. So there is for affine Kac-Moody algebra, there is also another tensor product on representations, which is called fusion product, and which actually gives a category which is equivalent to representations of finite dimensional quantum group. And that's a very non-trivial business, which is called Kazhdan-Lustig equivalence. But I wasn't talking about that. Okay, so I don't see any more questions. Let me see. Maybe I see. Just a second. Yeah, there are a couple more questions. For a monoidal category C, its Drinfeld center construction is unique. Also, the relation of Drinfeld double and Jeter-Drinfeld modules may hold for Hopf algebras in monoidal categories other than vector spaces. Yes, the construction is unique, and there is a construction of Drinfeld center in other monoidal categories. Definitely in symmetric monoidal categories, but even in braided categories, there is a construction like that. And it's very useful, actually. It's called relative Drinfeld center. And then there is a question, what's the corresponding structure of the R matrix under the Tanakian reconstruction? Yeah, so Tanakian reconstruction means that we pass from tensor category to a Hopf algebra. And then this R is called a quasi-triangular structure. So there is a axiom of quasi-triangular structure, which I didn't write down, but one consequence of that is the Yang-Baxter equation. And then that's a version under Tanakian reconstruction of the braiding. There are a couple more questions. Can you send the slides? Yeah, well, will the slides be posted?
We will post it, don't worry. We will post it.
Yes. And then there is a question. Is there a quantum group which cannot be written as a deformation of classical groups or Lie algebras? That's a very actually interesting question. Yes, there are some Hopf algebras. So there is classification of finite dimensional Hopf algebras is hopelessly hard, but there are some results about so-called pointed Hopf algebras. And in that case, there is a classification, at least when there is a abelian group of group-like elements. And there are some examples that don't seem to come from groups or Lie algebras. But if you ask about semi-simple tensor categories, few so-called fusion categories, this is a big question. So in fact, Drinfeld and Witten conjectured informally that all examples should be obtained from groups and Lie groups, from finite groups and Lie groups. But Van Jones conjectured that no, there should be new examples. It seems to me, it depends on the interpretation, but it seems to me that I agree more with Van Jones because there are some examples of categories which are called Hagerup subfactors, extended Hagerup subfactor, which don't look like anything coming from quantum groups. Although, because it is not a precisely defined notion, it is hard to prove that they don't come from quantum group because it is hard to even state the statement. Naive question, how is the Lie superalgebra version of quantum group theory different from the usual quantum group theory? Actually, it's just a special case. Like we said, we can define Hopf algebra in any symmetric monoidal category, and the category of supervector spaces is symmetric monoidal category. So this Lie algebras in this category are Lie superalgebras, and when we quantize them, we will get quantum groups corresponding to Lie superalgebras. So this is just a special case of this theory if you do it in symmetric monoidal categories. And then there is a question, could you say something about higher category theory, higher category analogy of braided tensor category? Yeah, there is higher category theory, and there are braided monoidal 2 categories, for example. which is a higher order notion. So there are actually many levels of things. But it's a kind of, it's hard to say two words about that. That's a very big theory. These braided monoidal two categories, for example, appear in applications a lot, and they're very interesting but complicated. Can you comment on the relationship of the Drinfeld Jimbo approach to the C-star algebra approach of compact quantum groups of Varanovich? Yes, there is this approach where you try to deform not the enveloping algebra, but you try to deform algebra of continuous functions on a compact Lie group. And in this case, you will get things which are called compact quantum groups. So this is basically a combination of a theory of quantum groups with some, there is some star structure, so unitarity structure, and also some analysis. And so this is a very nice subject as well. It's more analytic, but the algebraic, underlying algebraic structure is the same. Then, is it possible to parameterize the deformations of a monoidal category? Is there some unicity statement? Yes. There is a thing called Davidov-Yetter cohomology, which parameterizes deformations of a monoidal category. And third cohomology parameterizes infinitesimal deformations. Fourth cohomology parameterizes abstractions. And then if you take a Lie algebra or reductive group, or semi-simple group, simple Lie group, and its representations, that category, its cohomology is the same as cohomology of the group. In particular, third cohomology is one-dimensional, and fourth cohomology is 0. This means that there exists a unique deformation which is unobstructed. And that deformation is exactly one in the direction of quantum groups. This is described in the book on tensor categories, which I wrote with Jelaki, Nikšić, and Ostrich, which you can find on my homepage. Is there a classification of quantum groups? What's known beyond the ones attached to Katz-Moody algebras? Well, it depends on the definition. So if you talk about Hopf algebra, there is not much classification. For example, even for semi-simple Hopf algebra over complex numbers, there is a kind of open question of what they look like. Do they all come by a certain construction from finite groups? But it is not proved and not disproved, so it's not known. But in some settings, like pointed Hopf algebras, there is some classification in the case of abelian group of group-like elements. And it's quite complicated, but it's complete. So in Kitaev's 97 paper, fault-tolerant quantum computation, which addressed toric code model, points out that in generic G case, not subject to Z2, only the algebra of local operator D and the algebra of Riemann operator F has a structure of algebra and coalgebra. Is there any insight why this physical model has Hopf algebra structure? Well, I'm not really an expert on this, but I should say that this theory of topological phases of matter, which is a part of condensed matter physics, recently there was a lot of progress, and it was related to appearance of tensor categories and even higher categories in this story. They seem to be very kind of central objects there. To explain, well, I mean, the reason is somewhat similar to the reasons why it appears on three-dimensional topological field theory and topology, but hard for me to say more than that. But there is a lot of literature about this. So, yeah. Would you mind pointing out some reference you like for the higher categorical discussion? Well, I don't know much myself about this business, but right now at MSRI, there is a program about higher categories and quantum symmetries, 2 programs. And this is exactly about that business. And they produced a lot of stuff which is online, I suppose. So, so there should be some lectures. There was an introductory workshop there, for example, and the talks are recorded. So this should be publicly available. There were introductory workshop on both programs. And so this should be available. Now, can you comment on what you see as the basic difficulties faced in the theory of higher loops, say quantum toroidal Kac-Moody algebra and toroidal Hecke algebra? Actually, toroidal quantum groups is a new and very beautiful theory, but it's more complicated. One difficulty is that it's not as easy to split. Toroidal quantum group has kind of generators which are labeled not by integers, but by pairs of integers. So there is no natural ways to cut it into 2 halves, which is what you need to do to develop representation theory. But there are many ways. Actually, they correspond to rational numbers or even real numbers. And you can try to use all of them and compare them to each other. And that's how this theory works. For higher dimension than 2, I don't know any interesting results, but the 2-dimensional theory definitely exists, and it's quite rich. It's related to representations of double affine Hecke algebras and so on. Can you speak on the relation of quantum groups to quantum vertex operator algebras? Yeah, so the theory of quantum vertex operator algebras is not very well developed yet. I wrote a paper with Kazhdan 20 years ago, and then since then there were a number of papers by various people, such as Lee and some others. But one can define quantum vertex algebras attached to Yang-Baxter and quantum affine algebras. So the quantum affine story appeared relatively recently in the work of Molev and collaborators. And this is seems to be a promising direction, but not very developed yet. Could you comment on how GLQ is the double of a small quantum group, although in general the center construction P plus equal P minus in Z of yes. So I should say that besides these small, so small quantum group, there is small quantum group, and there are modular categories attached to quantum groups. It's a little bit different things. And modular category attached to quantum groups are not doubles of anything. In particular, they don't have P plus equal to P minus, as asked in this question. The Gaussian sums don't coincide, and the central charge is not equal to 1. And that multiplicative central charge is not equal to 1. There is a, so how does quantum group apply to lattice model? So there are nice books about this. So there's a book of Jimba and Miwa, which is called The Algebraic Analysis of Solvable Lattice Models, which explains that. But basically, it has to do with representations of affine quantum groups. So attached to Kac-Moody algebra of affinely algebra. But that's too complicated to answer right now. But I recommend this book by Jimba and Miwa, which is very nice. And Sasha Kirillov answered my question about Kitaev's model. The model with arbitrary size finite group G is part of an extended topological 3-dimensional quantum field theory, namely Turaev-Vera theory. And in any such theory, the category attached to S1 is a braided monoidal category. In this case, category of representations of the Drinfeld double of G. Okay, so it's a thank you, Shulik. So this is the answer. So basically, it kind of expands on what I said, that the reason is the same as it appears in 3-dimensional topological quantum field theory, but this is a much more precise answer. I think there are no more questions.
So that's good. So we should end now. It was a beautiful and nice lecture you gave, and we thank you very much on this. Tomorrow at 1 o'clock, there will be another talk by Robert Grice on sporadic groups, finite simple groups. So I expect to see you tomorrow at 1 p.m. Thank you again, Pavel. Okay.